Hello everybody. Today we want to introduce a new term to you called system temperature, and that's normally abbreviated as T sub S. So let's think about a typical fairly simple communication system. Let's assume that we have an antenna, in this case a dish, and it's pointed up here in the sky, and it's looking at what we call cold sky. There's nothing really hot in here. And to make things a little more complicated, we have what we call a low noise amplifier. And typically that's abbreviated as LNA. And this thing delivers energy to a load, typically a receiver. So let's go back to cold sky. Let's assume that we're doing a CubeSat and we're off the horizon maybe 30 or 40 degrees, and we're not looking in any particular constellation. We're just looking at typical background stars, and at this frequency, at this elevation, we typically think that the temperature, the noise equivalent temperature, is 30 degrees Kelvin. All right, now let's talk about this amplifier. All amplifiers make noise. And we characterize this noise as the equivalent temperature. So when you buy an amplifier or you design an amplifier, the two things that you design into this thing is the gain of the amplifier and how much noise it generates. And we can characterize that noise by an equivalent temperature. And typically a pretty good low noise amplifier at this frequency has a noise temperature of about 100 degrees Kelvin. All right. Now remember the equivalent temperature, if we were to take a resistor and heat it up to some temperature, this resistor, these electrons, excited electrons, this resistor will make noise. And of course this noise is proportional to its temperature. So now let's introduce what we call the system temperature, and that is really easy. The system temperature, T sub S, is equal to the sum of all these things that make noise. So, you know, we have the sky noise, the antenna noise, so it's 30 degrees. And the amplifier generates 100 degrees Kelvin worth of noise. So the system temperature is 130 degrees K. Now, knowing the system temperature, we want to calculate how much power is delivered into this load or this receiver. And remember, in the last videos we talked about Planck, and he figured out that that anything above absolute zero makes a noise, and he characterized that as the power in watts is equal to some constant, in this case Bosone's constant, times the absolute temperature in Kelvin times the bandwidth in hertz. Now the logarithmic function of this is, and if we want the power expressed in dBs, so we're going to write the log equivalent of this thing, the power in dBs, is equal to 10 times the log of this constant, K, B, T, and since we want it in dBms, it's referenced to 1 milliwatt, or 0.001 milliwatts. So now all we got to do is go back and plug into this thing. Now, all communication systems require some bandwidth, and we will try to deal with that in future videos. A typical CubeSat that's communicating at something, some data rate, typically is could be 25,000 hertz. What happened here? All right. So now all we got to do is go plug this thing in. So this thing works out to be 10 times the log of Boltzmann's constant, 1.38 times 10 to the minus 23, times the temperature, 130, times the bandwidth, divided by 1 milliwatt. Doing the math, this turns out to be minus 129.8 dBm. So this is the noise at this receiver with no satellite in view of the antenna, is that this thing will generate minus 129.8 dBm. If you don't like that number, there's a couple of things you can deal with. One is you can design a better amplifier. Instead of making 100 degrees Kelvin, maybe it makes 50. Or you can reduce the bandwidth. Now, each of these things has implications. If you reduce the bandwidth, typically you trade off data throughput. In other words, if you don't like this minus 129 dBm number, you can trade some bandwidth by some data rate by reducing the bandwidth. Remember, what we're trying to really do is we're trying to put a decoder out here, or a demodulator. So the demodulator responds to signal to noise. And typically, when we do this, is we also attach some bit error rate. So now we know the noise. In subsequent videos, we know how to calculate the signal. So now we are dealing with the signal and the noise, and now we start to see some trade-offs.